Let's talk about solutions to homogeneous linear systems of differential equations with complex eigenvalues. For the linear system dx dt equals 3x minus 2y, dy dt equals x plus y, compute the eigenvalues and the corresponding eigenvectors and find the general solution. First, let's find the eigenvalues for a equals 3, negative 2, 1, 1. That, of course, comes from the coefficients here. There's our matrix A. The eigenvalues are going to be the solution to the determinant of A minus lambda I equals 0. So here's A. We subtract lambda from everything on the main diagonal. We get this. Take the determinant. We get 3 minus lambda times 1 minus lambda minus 1 times negative 2 is 0. In other words, 3 minus 4 lambda plus lambda squared plus 2 is 0. So we have lambda squared minus 4 lambda plus 5 equals 0. That, unfortunately, doesn't factor nicely. So we use the quadratic formula. By the quadratic formula, the solution to lambda squared minus 4 lambda plus 5 equals 0 is lambda equals the opposite of negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 5 all over 2 times 1, which is 4 plus or minus root 16 minus 20 over 2. That's 4 plus or minus square root of negative 4 over 2. In other words, 4 plus or minus 2i over 2, or simply 2 plus or minus I. So the eigenvalues are lambda equals 2 plus I and lambda equals 2 minus I. Using Wolfram alpha, we can find that the corresponding eigenvectors, I know it seems like cheating. You can find the eigenvectors if the eigenvalues are complex. You can do that, and I've done it before, but it takes a lot of time. We're just going to use Wolfram alpha. Okay, so when we use Wolfram alpha to do this, here's how you do it. You go to Wolfram alpha, or really any eigenvalue or eigenvector calculator. This one's fine, for example, but you can find others. You go to Wolfram alpha, you just type in eigen, and it will prompt you with this. This comes up, so you just click on that. Or you just type eigenvectors. 3, negative 2, 1, 1. That's our matrix. It will tell you the eigenvectors of 3, negative 2, 1, 1, and it'll tell you those corresponding eigenvalues. We already knew those. Okay, so we find that the corresponding eigenvectors for those eigenvalues are these. Now, based on what we've seen before, our solution y of t is k1 e to the lambda 1t v1 plus k2 e to the lambda 2t times v2. First eigenvalue is 2 plus I, second eigenvalue is 2 minus I, and then we plug in the eigenvectors, and we're good to go. And technically, this is our correct solution. But it's not particularly helpful because, look at that. It's got i's running around in it. We don't want that. There is a way we can write this solely in terms of real numbers. Using Euler's formula. Remember this one? E to the a plus bi equals e to the a cosine b plus I sine b. Okay, so we're going to let lambda equals alpha plus beta I be a complex eigenvalue for the system. dx dt equals ax plus by, dy dt equals cx plus dy, with corresponding eigenvector v. Again, this is the complex eigenvalue, and this will be the eigenvector. The general solution to the system will be y of t equals k1 e to the alpha t times, holy cow, this is a messy expression, but that's okay. I'll let you use it on a test or quiz. I'm not going to make you memorize it. So y of t is going to be k1 e to the alpha t times the quantity real part of v cosine beta t minus imaginary part of v sine beta t plus k2 e to the alpha t, imaginary part of v cosine beta t plus real part of v sine beta t. Okay, so in this particular case, the eigenvalue is lambda equals 2 plus I, so we can see that alpha equals 2 and beta equals 1. This is our eigenvector, 1 plus I, 1. The real part of v is just going to be 1, 1. And the imaginary part of v is just going to be 1, 0, because here we have an I and there we don't have anything. So y of t is going to be k1 e to the 2t, again, that's our alpha, times this, again, we've got 1, 1 cosine t minus 1, 0 sine t, plus k2 e to the 2t, again, that's our eigenvalue. Then we've got 1, 0 cosine t plus 1, 1 sine t. And there we have it. That's our general solution to that system of differential equations.